In this paper, we proposed a new method called EXPRESS for adapting transformer models to few-shot tasks. Our method uses shallow and residual prompts to maximize adaptation expressivity, is highly parameter efficient, and is immune to catastrophic forgetting. EXPRESS significantly outperforms strong adaptation techniques on a variety of few-shot tasks, including classification tasks and semantic segmentation. EXPRESS also demonstrates the importance of prompt organization, outperforming other concurrent prompting techniques like visual prompt tuning with a much smaller computational budget. So the motivation for this work is to obtain models that can learn a variety of downstream tasks from a few training examples. These tasks could include natural categorization, or tasks from specialized domains like medical domain, or even structured prediction tasks like semantic segmentation. Now, to address the diversity in downstream tasks, we require a diverse and large-scale pre-training as well. That in turn requires a large pre-training dataset, typically known as the base domain, and a model that can leverage the base domain to benefit the downstream tasks via a shared latent space. Now, recently, transformers have been shown to scale more effectively with the base domain sizes compared to traditional architectures like convolutional neural networks. So our aim in this work is to adapt transformer models for few-shot tasks. Traditional adaptation techniques like full model fine-tuning is assumed to be a strong approach for adaptation. However, it has a few disadvantages when considering adaptation of large models in the few-shot regime. In particular, full model fine-tuning might not generalize well to test examples. It's also prone to catastrophic forgetting as it adapts all the parameters of the model. And it might scale poorly due to the massive parameter storage. Our solution is a parameter-efficient adaptation technique that uses two types of learnable prompts, namely shallow prompts and residual prompts, to maximize adaptation expressivity as well as prevents catastrophic forgetting of prior knowledge. The characteristic computation of a transformer is the multi-headed self-attention module. This module computes the token-wise output by performing a weighted aggregation over all value tokens, such that the weights are computed as a pairwise correlation between the query of the target token and the key of all tokens. The first step in EXPRESS is shallow prompting, where we append randomly initialized learnable tokens at the input. At each layer of the transformer, these prompts are processed via the self-attention module in the same manner described in the previous slide. A shallow prompt by itself has limited capacity. So to increase the capacity, we append multiple shallow prompts. However, beyond a certain threshold, increasing the number of prompts only increases the computational complexity while the performance saturates. So to further increase capacity, we introduce the idea of residual learnable tokens that are added to the query key value projections of the self-attention module. The residuals are only added at the prompt locations PI, but not at the patch locations ZI. We show in the paper how residuals modulate the weighting in the self-attention. By introducing residual prompts at every layer, we can leverage the hierarchical structure of transformer model, resulting in better few-shot performance with the same compute. The idea of residual prompting can be generalized to other computations as well, such as the layer norm and the multi-headed projection computation of the multi-headed self-attention module. Our final model consists of shallow prompts as well as 5 different types of residual prompts corresponding to each of the shallow prompt location. Each of these residual prompts are independently initialized. During adaptation, we only optimize the shallow and the residual prompts with a classifier head, leaving the transformer backbone untouched.
This by construction prevents forgetting of the prior knowledge which is encoded in the frozen backbone. Each of our design decisions regarding the prompting leads to non-trivial gains in few-shot performance. This results in a final model that significantly outperforms the base approach that only optimizes a classifier head. The number of prompt parameters with the classifier add up to less than 1% of the total parameters. Hence, our method is highly parameter efficient, that makes it suitable for few-shot adaptation and also allows it to scale well with the number of tasks.
We evaluate the effectiveness of various types of residual prompting on a fine-grained classification benchmark with few-shot training. We observed that within the multi-head self-attention block, each type of residual prompts yields significant improvements over shallow prompting. Within the multi-layer perceptron block, residual prompts are more effective for layer normalization computation compared to linear layer computations. Prompting multi-headed self-attention block is better than prompting the multi-layer perceptron block, and hence we use this setting for most of our experiments. One of the key results in the paper is the comparison of EXPRES with well-known adaptation techniques. We observe a trade-off between the few-shot performance and the immunity to forgetting over a wide variety of classification and structured prediction tasks. In comparison to other methods, EXPRES achieves a much better trade-off between the performance and forgetting, outperforming even the full fine-tuning technique by a significant margin of 7.5%. EXPRES also outperforms concurrent prompting techniques like visual prompt tuning with a significantly fewer prompt. This demonstrates the importance of prompt organization. On few-shot semantic segmentation tasks, EXPRES outperforms full fine-tuning by almost 25% and visual prompt tuning by 5%, reinforcing the effectiveness of residual prompting as a strong and generic adaptation technique. Qualitatively, EXPRES predicts the segmentation masks more accurately than other adaptation methods. Thank you, and we hope to see you at the poster session.